All right, it's been a long time since I've done a live stream. It's been a long time since I've done much of any programming outside of work, actually. Besides some uh, of my contract job that I have with another company. But uh, 12 and 23 came to a close last year. I didn't really do many streams at the end just because I was trying to just get it done, and I was also doing Advent of Code. I did do a couple streams on that, but then it got difficult, and I just kind of wanted to make progress on there. Anyway, this year, my main goal is to continue work on getting through Crafting Interpreter's book, which is a fantastic book for teaching you how to write an interpreter and a compiler. So that's my main goal this year. I'd like to be able to learn more about writing a compiler and hopefully at some point in the future have the opportunity to make my own programming language. I have a few ideas, one for a Forth-like programming language that's uses a stack machine and sort of like a postfix syntax. I have another one that's more like an ML in semantics, but has some other ideas on this syntax side of things. Um, those are the two main ideas, I suppose. Anyway, I actually took a stab at going through this book. I guess it's like a year and a half ago at this point. I was in the Philippines and had some downtime and started going through this book, but I'm kind of deviating a little bit from the book. The book is split into two parts. The first part, you're writing an interpreter for a programming language called LOX in Java. And I haven't done a whole lot of Java. I could probably keep up with it, but I'm also not really a fan of Java anyway. And some of the bits of it are I've kind of gone through the whole parsing lexing exercise a few times before. So I've kind of skipped ahead a little bit and I'm using some inbuilt features from OCaml. Oh, that's kind of the takeaway there is I'm actually instead of writing in Java, I'm writing the first part in OCaml, which I'm also not super familiar with, so I'm kind of learning on the go. So let's kind of just run through where it's been a while, so I'm kind of refresh myself where I am. So this first part just kind of gives a motivation of why to do this, and then has some how it's organized. I was thinking of at first of just kind of reading through the whole thing, but just in the interest of time, I'm just gonna kind of skip through and highlight the parts that are important for catching up to where I am right now. So he's talking about why he chose Java for the first interpreter. And then the second interpreter is writing it in C, and it's actually a compiler as well. So bring it down to like bytecode level or something like that. All right, so let's go to the next chapter here. Map of the territory. Parts of a language, it's talking about your analysis, syntax tree, parsing, token, scanning, source code. You have a tree walk interpreter. You do some optimizing with an intermediate representation. You do code generation to get bytecode or machine code. So that's kind of this idea here. So you got scanning and then parsing, and then you've got static analysis where you can do your type checking and things like that. Intermediate representations, optimizations, and then code generation. So whenever I've taken a stab at doing anything related to building my own programming language, I've kind of always got stuck at the lexing and parsing part. Not stuck as in I couldn't get past it, but that's as far as I would get, essentially. So I know very little about type checking or generating intermediate representations or any type of static analysis and optimization and such. I do a little bit know about the code generation side, but that's about it. All right, so I think we're doing a tree walk interpreter for the first section. And actually, I think I will at some point reread this bit because it's a really good book in teaching you teaching you all the things you need to know at a high level about a compiler and interpreter. So this is a language that we're building. It's essentially kind of a object-oriented C-like language. It's got dynamic typing, automatic memory management, the data types of booleans, numbers, strings, nil, expressions, arithmetic, comparison and equality, logical operators, precedence and grouping, statements, variables, control flow, functions, closures as well with lexical scoping, and then classes. I think class-based, it's either prototypal or classes. I think locked is a prototype. Nope. Okay, they're gonna do classes, not prototypes. Instantiation, initialization, inheritance, standard library. Okay. So let's take a look at a tree walk interpreter. Scanning. So here now it goes into taking your source code and chopping it up into the little bits that we'll need for, or the tokens essentially. So it defines the tokens here, left parentheses, right parentheses, left brace, right brace, all these stuff. And then stores location information, things like that. So here's what I'm actually doing. I'm actually just using built-in Lexer in OCaml. So we'll take a look at that in just a sec. Let me kind of do another scan through here. Lexical errors and such operators. Longer lexemes. Okay. So here's what I'm doing. Let's find this is our Lexer here. We have our tokens, which are defined in, where are our tokens defined? I suppose it's just right here. Okay. So here's our tokens here. Got our keywords here. And then we even have numbers, identifiers, white space, new line, and a file. And then there's a syntax error, legal character. So basically, this Lexer definition right here takes care of all the code that we just kind of scanned through there. Reserved words and identifiers. We already have those as well. Okay, challenge. Okay, so I did want to kind of take a look at this real quick. Lexical grammars of Python and Haskell are not regular. What does that mean and why aren't they? I'm not entirely sure the answer to that question, but an interesting point is I think this method of defining the Lexer in this MLL file and MLY file only works if you have a regular grammar. I'm not sure if that's true or not, but if I were to come up with a language that I wanted to write, oh, interesting. So now that I'm looking at this question again, it says Python and Haskell. Both of those rely on white space. Ah, okay, that's what it is. Yeah, okay. So there's this idea, regular grammars, I think, another way of saying that I think is called context free, which basically means you don't need to know all the information about where you are in the file to figure out the meaning of where you are right now. And that's not true of Python and Haskell because you need to know what indentation level, essentially it's stateful. Like it needs to keep track of like what indentation level I was at the previous statement in order to determine whether or not this statement or expression is part of that parent one or a child of it. So I think that's the answer to that question. And if that's the case, I'm not really a fan of white space dependent languages anyway, or I should say like indentation dependent. So I don't know if I'll really run into this in the future if I were to try and build my own language in this method. All right. Anyway, let's continue on. Representing code. So this goes into the AST of things and how you can represent it as a tree, context for your grammars, the rules for your grammars, and things like that. And then I think somewhere down the end of this, okay, here's our grammar here. So an expression is a literal, unary, binary, or grouping. A literal is a number, string, true, false, or nil. A grouping is parentheses surrounding an expression. Unary is a minus sign or a exclamation mark in front of an expression. A binary operator is an expression, operator, expression, and then operator are one of these. So we actually have those rules defined right in our parser. Oh, actually, here's where all the tokens are defined there. Okay, here it is. So an expression is a value, or let's see, that's a grouping. Okay, literal. So this is a literal. Literal is an expression. Oh, okay, that's what it is. L is left, bind operator is the middle, and then R is right. So that's a binary operator there, which we have as binary. Then we have unary, unop, and then we have grouping, and then I have literal as a value here. I suppose literal is probably better than value. Where do I have this defined? Okay, that's defined in the actual AST right here. There we go. Yeah, let's make that literal instead. And literal. That's going to mess up a whole bunch of stuff. But we'll get to that when we get to it. Okay, so now we want to change that out to literal here and literal there. Okay. Is there anything else where I have that value thing? Let's do a search for value. Go to AST. Okay, let's take all these and replace those with literal, and this gets replaced with literal, and that gets replaced with literal. There we go. And I'm just going to replace those two V's with L's. Okay. All right, so that's this grammar here. Okay, a literal then is a number string, true, false. So this now I want to be literal. Number, string, true, false, or nil. There we go. That's what we have. And then we have grouping is kind of actually, let's see. How do we have grouping? Grouping is defined there, but I think I just defined it inline. Yeah, I just defined it inline there. Unary is defined inline as well. Binary is defined. Binary operator. Binop is defined here. And then unop is defined there. Oh, they have operators here, which is what I've defined as binop essentially. And then unary is these two, which are actually defined here. Okay, cool. So let's just do what was the last thing I did? Do an exec. Okay, still compiles correctly. I think I'm gonna open it up again because, yeah, okay, all the red lines are gone now. Cool. All right. Let's get this, say, always on visible workspace. Make sure that's turned on. Okay, much better. Okay. So we got the syntax tree. The AST is defined in this file here in actual, essentially, types here. So we use types to define the AST, and then the lexer, the parser first defines all the tokens, and then those tokens are used in this lexer to scan and tokenize. Then the parser just have this program, which is just expression in the file. The parser then takes all of your tokens and puts them into the AST using the types from here. Cool. Disoriented objects, okay. Stem structure, nicely typed, and then I think at some point it then goes into expression problem and uses something called the visitor pattern, and this is all good and useful information, but again, I'm just kind of skipping ahead and using the inbuilt lexer and parser from OCaml, so I can get to the more interesting stuff of writing the interpreter and such. I do have a rudimentary pretty printer, and you can see that in this main thing. We've got parse, and then we've got print op, print control, print literal, print expression, and here I'm just taking some string, parsing it, and then printing the expression there. At one point I was trying to figure out how to write tests for this, and I remember running into some issues, so I ended up just kind of doing it inline in this main.ml file. So that's where we are here. Let's go to parsing expressions. Parsing game. I think that was just setting up the AST, and then this is actually writing the parser, so let's kind of skip down as well. Now there's also a lot of things in here for like catching the errors and such, and then presumably the lexer and parser that's built into OCaml have ways of surfacing those errors, but I haven't really dug into that yet. Okay, so this I think is where I left off so far. So you want to properly set the mood for this chapter. Try to conjure up a thunderstorm, one of those swirling tempests that likes to yank open shutters at the climax of the story. Maybe toss a few bolts of lightning. In this chapter, our interpreter will take a breath, open its eyes, and execute some code. There are all manner of ways that language implementations make a computer do what the user source code commands. They can compile it to machine code, translate to another high-level language, or reduce it to some bytecode format for a virtual machine to run. For our first interpreter, though, we're going to take the simplest, shortest path and execute the syntax tree itself. So essentially, what's happening is you're kind of embedding a language in the other. You're using all the features of OCaml to interpret and run the language that's embedded in it. So right now our parser only supports expressions. So to execute code, we will evaluate an expression and produce a value. For each kind of expression syntax we can parse, literal, operator, etc., we need a corresponding chunk of code that knows how to evaluate that tree and produce a result. That raises two questions. What kinds of values do we produce? How do we organize those chunks of code? taking them one at a time, representing values. In locks, values are created by literals, computed by expressions, and stored in variables. The user sees these as locks objects, but they are implemented in underlying language and our interpreter is written in. That means bridging the land of locks' dynamic typing and Java static types. A variable in locks can store a value of any locks type, and we can even store values of different types at different points in time. What Java type might we use to represent that? So we have a similar problem in OCaml. We're not doing this in Java, but OCaml is statically typed, and a variable, even though there's type inference, still needs to have a defined type at definition. So given a Java variable with a static type, we must also be able to determine what kind of value it holds at runtime. When the interpreter executes a plus operator, it needs to tell if it's adding two numbers or concatenating two strings. Is there a Java type that can hold numbers, strings, booleans, and more? Is there one that could tell us what runtime type it is? There is, good old java.lang.object. In places in the interpreter where we need to store a locks value, we can use object as a type. Java has boxed versions of its primitive types that all subclass objects, so we can use those for locks' built-in types. Okay. So here we have a bit of a conundrum. We can't quite do what they're doing here. For instance, well, we do have a Boolean, right? We have number and we have string, but we don't have a nil, and we don't have this object thing that can represent any locks value. So given a value of static type object, we can determine if the runtime value is a number or a string or whatever, using Java's built-in instance of operator. In other words, JVM's own object representation conveniently gives us everything we need to implement locks' built-in types. We'll have to do a little more work later when we add locks' notion to functions, classes, and instances, but object and the box primitive classes are sufficient for the types we need right now. Okay. So my guess is that we're going to have to look ahead a little bit and see how to do the functions, classes, and instances and such in order to figure out how to represent nil or any arbitrary locks value. But we'll kind of continue on here. Next, we need blobs of code to implement the evaluation logic for each kind of expression we can parse. We could stuff that code into syntax tree classes in something like an interpret method. In effect, we would tell each syntax tree node, interpret thyself. This is Gang of Four's interpreter design pattern. It's a neat pattern, but like I mentioned earlier, if it gets messy, if we jam all sorts of logic into tree classes. So they're going to reuse the groovy visitor pattern. In the previous chapter, we created an ASD printer class. It took in a syntax tree and recursively traversed it, building up a string, which it ultimately returned. That's almost exactly what a real interpreter does, except instead of concatenating strings, it computes values. Okay, we start with a new class. Evaluating literals. This leaves off the leaves of an expression tree, the atomic bits of syntax that all other expressions are composed of are literals. Literals are almost values already, but this distinction is important. A literal is a bit of syntax that produces a value. A literal always appears somewhere in the user's source code. Lots of values are produced by computation and don't exist anywhere in the code itself. Those aren't literals. So literal comes from the parser's domain. Values are an interpreter concept, part of the runtime's world. So much like we converted a literal token into a literal syntax tree node in the parser, now we convert the literal tree node into our runtime value. That turns out to be trivial. Expression.value. We eagerly produced a runtime value way back during scanning and stuffed it in the token. The parser took that value and stuck it in the literal tree node. So to evaluate a literal, we simply pull it back out. Is that true for what we have here? So now we're going to, we have print stuff. Now we're going to do eval. We're going to say let eval, and we're going to eval a literal. So essentially it's just pulling out the value that's there, is what they're saying. Now nil's going to be an interesting one. I suppose I could wrap the whole eval literal with a option, but I think that kind of defeats the purpose of this. What do we want to do about this nil for now? Let's return like 0 or something. Okay. String of string, number of float, boolean of bool, and then nil. I suppose this can just be nil itself. We just have a type called nil. So this isn't supposed to be, this is either a string number boolean, string float bool, or nil. What if I just leave this untyped for now? Doesn't like it, so it doesn't make a union of it. So let's say string float bool nil. Nope, doesn't like that either. All right. So how do I do this? I need a type that's the union of string of string, number of float. I think we want type value, and we just want this to be string float bool nil. Maybe this has to be, it does have to be capitalized, right? Float bool nil. Okay. Value. The expression is type string, but an expression with respect to type value. I remember getting kind of stuck on this last time of how do I actually evaluate the literal. So because essentially it's just pulling out the value, which is the equivalent of doing this. But I need to actually of type value. Well, the string is of type value, right? What am I missing here? Hope that didn't change anything. Type value is equal to Okay, let's do a little bit of Googling then. OCaml return type union. All right. How do we do enumerated data types? Okay. Type aliases. Latitude, longitude is float and float. But if I want to do a let's see, type value is string. Let's just see what that does, for example. Now if I did plus, doesn't like that. Doesn't like that either. Float. The type constructor float expects 0 arguments, but here it's applied to 1 argument. Type value, type latitude longitude is equal to float times float. I might be better off skipping the eval literal and actually going to evaluating something else, like parentheses or unary expressions. So let's give that a try. Evaluating parentheses. So let's do I think I call it grouping. Okay, that's exactly what I want. This pattern matching is not exhaustive. Here's an example of case that's not matched. Aha, okay. Oh, I see. So eval expression needs the whole thing. So let's do literal identifier binop I don't want to do that whole thing. Let's just do... Let's get rid of that. Grouping. Okay, let's do unop and control. That should be exhaustive now. Okay. Alright, so right now I've done next to nothing here. All I've done is unwrapped the grouping. So that's actually more or less what evaluating in parentheses is right here. Except for what we'll actually have to do is eval expression E. And we have to mark this as recursive. Okay, there we go. So grouping is done. Let's do evaluating unary expressions. Like grouping, unary expressions have a single sub-expression that we must evaluate first. The difference is that the unary expression itself does a little work afterwards. Okay, so if it's a minus, then that we're assuming that that operates on a number. The sub-expression must be a number. Since we don't statically know that in Java, we cast it before performing the operation. This type cast happens at runtime when the minus is evaluated. That's the core of what makes the language dynamically typed right there. You can start to see how evaluation recursively traverses the tree. We can't evaluate the unary operator itself until we evaluate its operand sub-expression. That means our interpreter is doing a post-order traversal. Each node evaluates its children before doing its own work. Okay. So let's do a... Do I actually have a separate... I have print op. AST is made up of operators. Only in the parser do I have them kind of split up into unop and binop. Do I want to split that up? Probably should. Alright, we're gonna not do that for now. I'm going to let eval op No, we can actually do better than that. We can say unop. Eval unop, which will be op and expression. Ooh. That's pretty good. That looks like it will work. I love how that did that for me there. Eval unop. So let's just do eval unop there. Unop op e. There we go. This expression has type A, B, but an expression was expected of type expression, op, expression. I think I need to remove that comma. There we go. Okay. Pretty good. Let's see if I can evaluate something. Let's evaluate -2. Parse and then eval expression. And then how do I print? I guess I can just say what's this yelling at? This expression has type expression, but expression is expected to type unit. Okay. How do I just print any arbitrary value in OCaml? OCaml print. Well, in this case, I'm going to do print float for now. Oh, okay, because it's actually eval expression is now spitting out another expression still. So I think we can just print expression then. Okay, let's give that a try. There we go. There's a -2. So it's been evaluated. If I were just to put 2 there, actually, what am I expecting that to do? I'm still living in this expression land. I suppose that's fine. I guess, yeah, I guess that's fine. Okay. Um, okay, let's do the binop thing then. Let's do let eval binop, and this will need our left expression, operator, right expression, and here we're doing if it's a number and a number, add, subtract, multiply, divide, equal, not equal, greater, greater, equal, less, less equal. Okay. I'm supposing that the plus in locks is also supposed to add together strings. Oh, we also haven't done truthiness and falseness yet. So we'll do that in a bit. I just kind of want to evaluate a binop real quick. Eval binop, and we're going to take out the commas, and we're going to do a 2 plus 3. Hey, look at that. We've got an evaluator. That's pretty cool. 2 minus 3. Okay, I kind of guessed that would happen because with the minus there, and I wasn't sure if it was supposed to be appended to that Yeah, interesting. 2 minus minus 3. Let's give that a try. 5. Cool. All right. So truthiness. So I think what we need to do is, okay, so if we say false and put a not in front of it, not false, that should evaluate to true. Okay, that's good. So that is working, but we also need to do this truthiness thing. So in other words, whenever we negate a literal, if it's not a Boolean, then we need to, so in other words, if this is not and the literal is, or actually, oh, interesting. So I'm not even, can I put a not in front of, no, I can't put a not in front of anything other than the literal. So it still has to be a literal. But if it's anything, so if it's literal nil, actually that's what I wanted to find out. Ruby simple rule is false and nil are falsely and everything else is truthy. So if I'm negating nil, then I'm returning Boolean true. If it's anything else, then I want to, anything else would be, when I negate it, would be truthy, so it becomes false. I think that's true. Okay, so let's just make sure negating false is still true. Negating nil is true. Okay. Negating anything else, like a 1, is false. Okay. Negating a string of, I don't even know if I have strings in there or not. Cool. Negating anything else gives you false. Okay, so we did this bit. We are evaluating binary operators already. There's probably some stuff that we're not doing. Yeah, okay. So plus, if it's numbers, then it has to add them. If it's strings, then it has to concatenate them. Okay. So let's give that a try. Let's do literal string, add literal string, concatenate. Cool. So now we should be able to concatenate things. We'll concatenate hello and world. Look at that. Concatenation happening. Very cool. I presume we're actually supposed to also cast them to strings if they're anything other than, yeah, that's right. The plus operator can be used to concatenate two strings. To handle that, we don't just assume the operands are a certain type and cast them. We dynamically check the type and choose the appropriate operation. This is why we need our object representation to support instance of. Now my question is, what happens if you try and add a string to a number? Is it supposed to turn the number into a string, kind of like JavaScript does? Doesn't look like it's doing that right now. Okay, so we got comparators, quality. Oh, okay. So the equals bit, we can't just use the equals because we don't have truthiness built in. So let's let's build our isTruthy thing then. Like truthiness, the equality logic is hoisted out in a separate method. So what is Locke's notion of equality then? Unlike comparison operators, which require numbers, the equality operators support operands of any type, even mixed ones. You can't ask Locke if 3 is less than 3, but you can ask if it's equal to it. Like truthiness, the equality logic is hoisted out into a separate method. This is one of those corners over the details of how we represent Locke's objects in terms of Java matter. We need to correctly implement Locke's notions of equality, which may be different from Java's. Fortunately, the two are pretty similar. Locke doesn't do implicit conversions in equality, and Java does not either. We do have to handle nil-null specially, so that we don't throw a null pointer exception if we try to call equals on null. Otherwise, we're fine. Java's equals method on Boolean, double, and string have the behavior we want for Locke's. Okay, so that's the question is, do we have that working okay here? Invalid binary operation. It is equal, equal. Equal and equal, equal. Okay. Did I use a correct binary operator here? Let's go to the AST operators. We have equal there. The parser makes equal, equal into equal. There we go. Okay, that's fine. Because regular equal is for assignment. So we have a fatal error, exception, invalid argument, invalid binary operation. Because we did string equals equals string. Okay, so let's take this guy and just make it literal. Or actually we'll make it left and right. And then we'll say the Boolean of left equals right. Okay, good. Let's see if 1 equals 1. Let's see if 1 equals false. Let's see if 0 equals false. Let's see if nil equals false. Let's see if false equals false. Okay, I think we're good there. So let's do the same thing for not equal. And greater than, less than. Are those supposed to be comparison? Okay. Comparison is only for numbers as well. So let's put all the number stuff together. Let's put the string stuff down here. And then this is generic stuff. Okay. Pretty good. So, I can't forget that we've skipped the literal stuff, and maybe that's okay, actually. Let's keep going, though. Equality, we've got truthiness, runtime errors. Okay, let's read through this a little bit. It's cavalier about jamming casts in whenever a sub-expression produces an object and the operator requires it to be a number or string. Those casts can fail even though the user's code is erroneous. If we want to make a usable language, we are responsible for handling that error gracefully. It's time for us to talk about runtime errors. I spilled a lot of ink in the previous chapters talking about error handling, but those were all syntax or static errors. Those are detected and reported back before any code is executed. Runtime errors are failures of the language semantics demand we detect and report while the program is running, hence the name. So let's say we want to trigger a runtime error. Let's say false is equal to true, but in quotes. Actually, I think it's still okay with that. Let's see, let's put that's actually going to be a parsing error. Anyway. All right. Right now, if an operand is the wrong type for an operation being performed, the Java cast will fail and the JVM will throw a class cast exception. That unwinds the whole stack and exits the application, vomiting a Java stack trace onto the user. That's probably not what we want. The fact that locks is implemented in Java should be a detail hidden from the user. Instead, we want them to understand that a locks runtime error occurred and give them an error message relevant to our language in their program. The Java behavior does have one thing going for it, though. It correctly stops executing any code when the error occurs. Let's say the user enters an expression like this. You can't negate a muffin, so we need to report a runtime error at that inner expression. That in turn means we can't evaluate the divide expression since it has no meaningful right operand. Likewise for the star. So when the runtime error occurs deep in some expression, we need to escape all the way out. We could print a runtime error and then abort the process and exit the application entirely. That has a certain melodramatic flair. Sort of the programming language interpreter equivalent of a mic drop. Tempting as that is, we should probably do something a little less cataclysmic. While a runtime error needs to stop evaluating the expression, it shouldn't kill the interpreter. If a user is running the REPL and has a typo in the line of code, they should still be able to keep the session going and enter more code after that. Detecting runtime errors. Our tree walk interpreter evaluates nested expressions using recursive method calls, and we need to unwind out of all of this. Throwing an exception in Java is a fine way to accomplish that. However, instead of using Java's own cast failure, we'll look at a lock-specific one so we can handle it how we want. Before we do that, we check the object's type ourselves. So for unary, we add check number operand. The code to check the operand is such and such. When the check fails, it throws one of these. Okay. Runtime error, token string message. Unlike the Java cast exception, our class tracks the token that identifies where in the user's code the runtime error came from. As with static errors, this helps the user know where to fix their code. We need similar checking for the binary operators. Oh, Peter's online. Hey, Peter. Unlike the Java cast exception, our class tracks the token that identifies where in the user's code the runtime error came from. As with static errors, this helps the user know where to fix their code. We need similar checking for the binary operators. Since I promised you every single line of code needed to implement the interpreters, I'll run through them all. Greater than, or equal to, less than equal to, subtraction, okay. All those rely on this validator, which is virtually the same as the unary one. Throw new runtime error operator, operands must be numbers. Okay. So we can do something similar to this. Let's say, for instance, this unary operator, we have a negate, and we catch it early. We say negate, but then the literal was not a number. So the literal was pretty much anything else. then we should return back an invalid argument and say we'll just say something like, well, actually, what do they say? Operands must be numbers. What did they use for the operand must be a number for the negate? Okay. Operand must be a number for negation. Okay. So now if we try and negate a false, for instance, we get invalid argument, operand must be a number, but we're not getting a very good stack trace sort of thing. I'll probably come back and revisit the issues with that. For not, we can pretty much negate anything. So I think this case will actually never be reached. And then we've got to do similar stuff with all the binary operator stuff. Okay, I'm gonna skip forward a little bit more. Hooking up the interpreter to visit methods. The visit methods are sort of the guts of the interpreter class where the real work happens. We need a rapid skin around them to interface with the rest of the program. Okay. This is another of those pieces of code like isTruth that crosses the membrane between the user's view of blocks, objects, and the internal representations in Java. Okay. Reporting runtime errors. Okay, so we're kind of just like holding on to the object. If a runtime error is thrown while evaluating the expression, interpret catches it. This lets us report the error to the user and then gracefully continue. All of our existing error reporting code lives in the logs class, so we put this method there too. Line error token line. Add runtime error true. We use a token associated with a runtime error to tell the user what line of code is executing when the error occurred. Even better would be to give the user an entire call stack to show how they got to the executing that code. But we don't have function calls yet, so I guess we don't have to worry about it. After showing the error, runtime error sets the field. Okay. So I think what I'm going to have to do is extend the tokener, tokenizer, and the parser to keep track of line number and column number and such and what token it's on. Unless it's already built in, so I'm going to have to investigate that a little bit more. Running the interpreter, mocks can start it. Scanning, parsing, and execution. Cool. All right, I'm going to peruse this document a little bit further, but got a lot further than I did before. I'm glad to be able to pick this up again and get an interpreter working here. So we've got, let's say, 2 times 3, for instance. And grouping should work. Whoa. What's going on here? Negate literal. Did it not catch the 2 plus 3? I don't know. Whoa. It seems to be always if it's negate in any literal. Okay, let's comment that out for a sec. 2 plus 3. So we should be able to do precedence as well now, or parentheses. So say 2 times 2 plus 3 should give us 10. Nope. Okay. All right. Well, I've got some work to do, but I'm going to call this it for tonight, and we'll revisit this soon. See ya.